All right, we're going to go ahead and get started. I'm Toran, I'm from Styra, I work on Open Policy Agent, but today I'm introducing David Zhu from Google and Jan Šafránek from Red Hat, and they're going to talk about Kubernetes Storage 101 and break down some really important concepts for you guys. So go ahead.
All right, hi everyone. Thank you for coming to our Storage 101 talk. So let's just get started then. So first of all, Kubernetes. I'm sure since this is the second day of the conference, you already know what Kubernetes is. But basically, it's like a container orchestrator, but we like to think of it as a pod orchestrator because it actually works on pods, which are collections of containers, right? And so, as we may know, containers are generally stateless. They're cleared on exit, but this is unless persistent storage is used. So that's what we're going to be talking about today. So here is an example of a pod, and this is actually a stateless pod, right? It's just got a MySQL image, and notice that there's no storage-related concepts in here. And what happens is that this pod actually, on exit, the entire database is cleared. And pods actually are quite ephemeral. They can, go down for any reason. They can go down because of preemption, so another pod with a higher priority comes in. Or they can go down just because the node went down. So this MySQL database is not going to be very resilient. So that's why we introduce some storage concepts in Kubernetes. So we have these three main objects here on this slide, the pod I just introduced, and the two main storage objects that we're going to be talking about. One is the PersistentVolumeClaim. And this is the application's request for storage. So the user will put this on the system to request for storage. And the persistent volume. This is the kind of the admin object for storage. So this is how the admin will create a pointer to actual physical storage. And it will contain all the gory details of our underlying storage. And these two objects kind of bind together. And don't worry, we'll talk a lot more about these in the future in detail. I just wanted to introduce them right now. So you might be asking, okay, so if I want storage, I just want a volume, right? I just want a disk that connects to my container. Why do I need two objects? Why do I need a persistent volume claim and a persistent volume? Well, by separating these concerns, the concerns of the user and the concerns of the admin on the other side, we're able to get both application portability as well as a little bit more security, right? So let me talk a little bit more about the portability side. Since the persistent volume claim only contains very basic information that the user workload requests of storage, so we'll talk a little bit more about what is inside it later, but it only contains very basic requests. You can make these types of requests on any type of cluster, on any type of underlying infrastructure, right? And the persistent volumes, which the admins create that are not portable, these ones are different per cluster based on your underlying infrastructure. When you create these persistent volumes, they contain all of the details about the underlying storage. Like, for example, if you're using an NFS storage underneath, this would contain things like your credentials and the IP address with where to find this NFS. And the security concern is also you don't want your users to be able to kind of create these persistent volume objects that reference underlying storage, because generally you don't want users to be able to just point to whatever underlying storage they want to, right? In the case of NFS, you don't want them to just put some random IP address and find whatever. Okay, a third object that we'll be talking about today is the storage class object. Jan will be going into more detail about this later, but basically what you need to know now is that this is for dynamic provisioning. It's a collection of persistent volumes. So if we take a bunch of persistent volumes, group them kind of by class, this goes all under one storage class type object. And we'll also use this to provision things dynamically. All right, so in a little bit more detail, I'm going to be kind of role-playing as the workload or the user in this case. So I am trying to put this MySQL pod on my Kubernetes cluster, and I want it to actually persist data instead of when it dies because it's an ephemeral pod, I don't want the data to go away. So I'm going to persist it, and I'm going to use a persistent volume claim. So we can see here that in this container, we have some volume mounts, and we've specified the data volume, and we want it to go into this path, into the container, okay? And we've also defined in the same YAML file, actually, what this volume is. And we've just defined this volume as a pointer to the PersistentVolumeClaim that we're going to reference, okay? So what does this PersistentVolumeClaim that we're referencing look like? Here's the name that we're referencing. And as I told you before, it's actually very simple, right? It actually only contains the most basic information that we need for our storage. So we only care about, we don't care how our storage is given to us or what underlying volume we have. As a person putting this workload onto the cluster, all I really care about is the size, things like what type of file system, or whether I want block, or the access mode, right? So there are many such parameters, but basically they're just the ones that the workload cares about, okay? So for example, in this one, I want 1 GB of storage, and I want it in read-write mode, okay? And I don't really care about the rest here. So in order to create this claim on the cluster, you just do a kubectl create -f, which is for the file, and we have the claim.yaml that we just showed earlier. And we can also get the PVC, and this gives us some more information about the PVC on our system. Okay, we can also create our pod, and we'll see that since the PVC has been created, it has something to reference, and the pod will start running. Okay. A quick debugging thing for PVCs, if you just get the PVC, sometimes you'll note that it's pending, and you won't know why. It doesn't, note how this doesn't actually say anything about why the PVC is pending. Really important to know, describe your PVCs, okay? Describe all of your API objects. When something goes wrong, you should think kubectl describe, okay? So when we describe this, we get some events at the very bottom, and this actually lets us get into kind of what the actual issue is here. So the actual issue here is that our storage class is not found, right? So kubectl describe. And now Jan.
So PersistentVolume is the first object that is for administrators, so I will play administrator in this talk. The PersistentVolume is just a bunch of metadata and pointer to the real storage. Kubernetes supports, I think, 15 different volume backends right now. All of them are hard-coded in Kubernetes, so if you want to introduce new backend, you need to go to Kubernetes code and write it there. And we kind of declared stop on new volume plugins, and instead we provide 2 extension mechanisms, how to connect Kubernetes to a different storage backend that's not listed here. We provide old Flex, and new fancy CSI, container storage interface. So you can connect Kubernetes to a storage backend that Kubernetes doesn't know anything about it. If we look at the details about the metadata, Kubernetes needs to know the capacity of the volume, how the volume can be accessed, and to which storage class it belongs. So this is some cheap storage on my old NFS server running somewhere in my infrastructure. So I created a storage class called cheap. And the last bit that's sort of mandatory is what should happen when this persistent volume is not needed, when Kubernetes is done with the volume and it should do something. We will cover that in detail later. So the persistent volume is just pointer to some storage perhaps outside of Kubernetes. And the last bit that's also created by cluster admin is storage class. It's basically a collection of persistent volumes that share some common characteristics like speed, so I can have fast storage class and slow storage class, or price, so I can have expensive storage class and cheap storage class, or I don't know, replication characteristics, so I can have a safe storage class with 3 replicas of data, or unsafe storage class with just 1 replica of the data. It also contains parameters for dynamic provisioning that is used when when there is no available persistent volume, but Kubernetes needs some, so it reaches some storage backend and provisions the data volume automatically. it needs to know whom it should talk to. It's the provisioner parameter, and you can find the exact values you can put here in either in Kubernetes documentation or in documentation of storage backend if you use CSI or any external provisioning support. And the provisioner usually needs some parameters that will provision a persistent volume of this given class. So this class is called fast, and these parameters will provision the fastest volume that is available on AWS. The parameters are different for each storage backend. That means this object is not really portable. If I take this runs on Amazon, I can't take it on GCE. It will not run there. I will need to provide different provisioner and different parameters. And each cluster, I strongly recommend, should have one default storage class. Default storage class is a class with this magic annotation. And what happens is when user, like David, creates a persistent volume claim without referencing any specific storage class, he will get the default one. So in this case, if David creates a claim without any storage class, he will get the fast one. The persistent volume can be created in two ways. The first one is dynamic provisioning. You should use that in your clusters, where administrator just creates a storage class, and when user creates a persistent volume, it either references a concrete storage class or no storage class and gets the default one. And Kubernetes then goes and creates a volume on the storage backend and a persistent volume object in Kubernetes pointing to it. Kubernetes then binds the persistent volume and persistent volume claim together, and nobody can use the persistent volume except the user through the claim. Nobody else can reach the data, at least from Kubernetes. And user can finally run some pods using the persistent volume claim. The other option we support is manual provisioning, where I, as administrator, can create a persistent volume object in Kubernetes pointing to some storage outside of Kubernetes for typically some legacy data that are pre-populated, and I want to use them in Kubernetes. And user creates exactly the same persistent volume claim like before, referencing some storage class, and Kubernetes will find the existing volume and bind it to the claim. Important note here is that Kubernetes always looks for the existing volumes first, and if there is no existing volume that would match the claim, only after that it goes and dynamically provisions the volumes. That means if this is some pre-populated data, some volume with pre-populated data, I should probably create a special storage class so somebody accidentally doesn't create a persistent volume claim requesting basically empty volume and accidentally binds to the volume with the data. So this is really for like brownfield scenarios where you want to use some old data in Kubernetes. You should use dynamic provisioning for the rest. Your life will be much easier. And when a user creates a pod, user can delete a pod or something can delete the pod. The data are still retained. User can create as many pods as he wants and still use the data. That's fine. And when user doesn't need the data, he deletes the persistent volume claim. That's the signal to Kubernetes. I don't need the data. Do something about that. And what happens is encoded in persistent volume reclaim policy field in the persistent volume I showed you before. We support 3 policies. We support recycle. We support it only on NFS. Kubernetes basically deletes all the data from the volume and puts it back to available state, so it's available to a different claim. It's kind of clunky. It doesn't work well with different NFS servers and so on, so it's deprecated. It may work for you, but expect troubles. The more useful policy is delete, when Kubernetes just goes to the storage backend, deletes the volume there, deletes the persistent volume object in Kubernetes, and the volume is deleted. Or you can use policy retain, where just Kubernetes puts the persistent volume aside. Nobody can bind to it because there can be, I don't know, credit card numbers on the volume. But the data is still there, and I, as cluster administrator, can reach the data or bind it manually to a different persistent volume claim. If David comes, asks nicely, I can give him the data. In all these three cases, the data are lost for the user. So user can't access the data. He either can go to me and ask nicely, or the data are deleted. So be very careful when deleting PVCs. You will lose your data. And finally, I, as an administrator, can delete persistent volumes manually. It could be useful in some cases, but again, be very careful. You are dealing with some data. Don't make users angry. Important note here, if you delete persistent volume in Kubernetes, the object, it doesn't delete the data in the storage backend. You must do that as a separate step. So now that you know all these Kubernetes objects, it's the time to show you how to use them in reality.
Right, so we've learned about the pod, the PVC, and the PV. But actually, we don't recommend using pods in production environments. And that's kind of because pods are not really for end-user production, right? They're kind of ephemeral. I alluded to this earlier, right? They can be kicked off for many different reasons. And when your pod gets kicked off of your machine, you actually don't have access to your workload or your data anymore. So if you're running a service on that pod, you can no longer hit it when your pod is gone. So how do we fix that? Well, we have some higher level objects in Kubernetes that can help you with your issues here. We have the deployment, which basically just runs many replicas of your pod template. So you give it a pod, and it just runs X many of them, right? And when your pod gets deleted for any reason, like someone comes in and preempts your pod from a node, the deployment will actually go and recreate that pod for you. So if you want 3 replicas, you're kind of always going to get 3 replicas eventually. We can scale this up and down. We can have more, less. But one of the big caveats with the deployment, for storage especially, is that all of the pods in your deployment share the same persistent volume claim. So this is kind of what it ends up looking like. You have your deployment, which spawns multiple pods, but they all reference the same persistent volume claim. And as we know from the previous slides, that means that it will reference 1 persistent volume, which means we'll get 1 underlying storage, right? And you might already have some clue as to why this might be a problem, right? So all 3 of these pods are writing to the same volume, writing and reading from the same volume. So unless your workload is specifically designed to do this, to write and read to the same volume, it's very likely that they're going to overwrite the data of each other, right? And this generally causes applications to misbehave in different ways. We've seen crashes. There are a lot of cases where if your volume is read-write once, your pods will not actually come up on a second node or a third node because you can only attach them to 1 node. So you could have a lot of issues with a deployment like this while using stateful volumes. But there is probably a case where you do want this, and you have to be aware that this is exactly what's happening, right? So if that doesn't exactly work, well, we have another type of high-level object for you to use, which is called a stateful set. So this does a very similar thing in that it creates many replicas of your pods. It has all the same it does similar things where it goes, you can scale it up and down. When the pod dies, you can put a new one in. But the main difference here for storage specifically is that each pod will now get its own persistent volume claim. And the way we do that is in the object, you actually specify a PersistentVolumeClaim template, and that templates out the PVC, and each pod will get like kind of a stamp out of that template. Right? So this is kind of what it ends up looking like in a 3-pod case. We have 3 pods here and 3 PVCs, each one connected to a pod. Right? So in this case, each pod gets its own volume. And this is generally more like a good starting place for what you want. Right? But unfortunately, Kubernetes doesn't really handle your application needs. So when you're using a stateful set, it's very important to keep in mind that you still need to come up with the mechanism, sort of, to have these pods be aware of each other and be in the same member set so that they can do leader election or run in some sort of active-passive, active-active mode. But Kubernetes does not do this application-specific synchronization between your pods, right? So you can use a stateful set as a building block for your workloads, but in the end, you still need to kind of determine how these pods interact with each other and who gets to serve data, who gets to write data. This all needs to be determined by the application. Okay? And now Jan will talk a little bit more about some storage features.
In Kubernetes, we accumulated a lot of features. This is not a complete list, what I'm going to present. This is just a very high-level overview, what you can use, and you can mix and match all the features together and build your stateful applications. So the first feature is topology over scheduling. Until now, we sort of expected that if we have persistent volume object in Kubernetes, we expected that the volume is available to all nodes in the cluster. If you run a cluster across multiple availability zones in cloud, that's usually not the case. Persistent volume is then available only to subset of nodes. Kubernetes can know about that using topology over scheduling and schedule pods to nodes where the data is accessible. And we also introduced something we call delayed provisioning, where if user creates a persistent volume claim, it's not provisioned immediately because it could be provisioned in a wrong zone. But we wait until user creates a pod, and then scheduler looks at the pod requirements, like it needs a GPU, it needs 8 cores, it needs 5 gigabytes of memory, and the claim, it needs like, I don't know, 10 gigabytes of storage, and schedules both the pod and the persistent volume claim to a node that has enough storage and has enough CPU power and GPUs. So in reality, you can create a persistent volume claim and find out that this pending. And the reason for pending is that it is waiting for the first consumer. And after you create a pod that uses the claim, or you create a stateful set, of course, not the pod, only after that the claim gets bound. So don't panic if your claims are pending. This may be the default mode in your cluster, especially if you run across multiple availability zones. There is a talk later today. Michelle is covering it in a bit. Other feature we have, local volumes. If you have some spare hard drive or SSDs attached to your nodes, you can use them as persistent volumes. Of course, you get super extra speed because you are using local storage. But the trade-off is that if the hard drive is broken or the node is broken, your data is lost. So maybe that's what you need, but for generic storage, be aware this is dangerous. This could be dangerous. It's useful mainly for caches and this kind of stuff. You don't really mind if they get lost. Until now, if you used a volume in a pod, Kubernetes created a file system on it and mounted it inside the pod. There are some workloads that don't like it. They want extra speed, or they want to handle the block device by themselves. So now you can use raw block devices, and you can get a raw block device inside your pod, and you can do whatever we want with it. Kubernetes won't touch any data on the volume. You can also resize your volumes. If we support only expansion, you can increase the size. You can't shrink it. Currently, what we have as beta feature is offline resize. That means that Kubernetes resize the volumes, but you must stop your pod first. So if you have a stateful set, you scale it down, resize your volumes, scale it up, and new pods will have bigger volumes. We are working on online resize. That means that you won't need to resize to stop the volumes at all. We have it as alpha. You can try it and fill bugs and bug fixes. Inline volumes. Initially, it was not on these slides because it's damn dangerous. But you don't need to use persistent volume claims and persistent volumes at all. You can reference a volume directly in a pod. We call them inline volumes. They are inline in the pod. So this pod runs some test container, and the test container gets mounted this Amazon volume. This makes the pod completely not portable. You can't take the pod and run it somewhere else because the volume is not there. But maybe that's what you want. You need to just test something or run a job. It is usable. What's more usable for inline volumes are ephemeral volumes. Maybe you already met them in Kubernetes. We use config maps and secrets and downward API, where you can get a configuration or some secrets, usernames and passwords, or SSH keys as files inside your pods. You can create API object called config map or secret, which are basically key value. This is a key value store. And for each key, you get a file on a file system inside your pod, and the value will be saved as data in the file. This is useful for distributing usernames and password, or I personally use it to distribute SSH keys. These volumes are not persistent. You basically can't write to them because it gets overwritten by the value from API server. And the last feature is container storage interface. That is David's.
Yes. We also have some new features to talk about. Some of those that Jan talked about were new as well. But we have the container storage interface, which is an industry standard that kind of enables storage vendors to write a storage plugin once and deploy it anywhere. So a lot of different container orchestrators have implemented the container storage interface, and they're all going to interface with the same drivers. So Kubernetes as well, we've implemented support for CSI, and we have a growing number of drivers in the ecosystem. I believe it's over 30 now that we're aware of that you can use in Kubernetes. So from the user perspective, there's actually no change whatsoever. You still use the pods and PVCs that we've been talking about as usual, but this adds some extra work to the cluster admin, which we've written up here, but not only extra work, it adds a lot of benefits as well, right? So the benefits of the container storage interface are going to be, well, it's an extensible plugin framework for your storage drivers, right? So now these plugins are not in the system itself. If they crash or something, you're not going to bring down all of Kubernetes with it. The vendors are going to be able to push out more frequent updates to their drivers that you as a cluster admin can pull in much quicker, as well as many other benefits that come with having a plugin interface instead of what we had before, which was all the plugins being built into Kubernetes. Another feature that we're actively working on that is currently alpha is volume snapshots. So this is a part of the container storage interface. Basically, it lets you take a snapshot of a PVC at a point in time. And we get the snapshot, and then we can then provision a new volume based on that snapshot and use it later in a different pod or the same pod or something. Okay. We have one final feature to talk about, which is CSI Migration. This is still also in alpha, but this is a push to kind of deprecate sort of the in-tree plugins. The API is going to stay. If you're using in-tree plugins today, I want to make it very clear that you can still continue to use those in the future. But what we're doing is actually removing all the backend implementation and shimming that to the CSI driver. So as I mentioned, the container storage interface before, 30+ drivers, more frequent updates, better security guarantees. We're shimming the backend to that. So you can still use the same in-tree plugin interface. OK, so to summarize, the main takeaway that you should have from this talk is this image, right? There are two main parts of the storage system in Kubernetes, right? We split it out into administrator and into user workload. And we have the persistent volume claim for the user request, and we have the persistent volume for the administrator for all of the gory details of your underlying storage, okay? And also we have the storage class, which kind of groups persistent volumes together, and we can use that for dynamic provisioning. These are the main concepts. We also have those higher level workloads, deployments, stateful sets, and all of those features you can look up documentation for online. So that's not all. We want to, if you're interested in storage, we have a ton of talks about storage at KubeCon. About half of these actually have already finished, but I want to call out if you're interested in contributing or interested in more about what we're working on currently, I would recommend coming to the intro deep dive for the Kubernetes Storage SIG. And of course, if you're interested in any of these other specific storage-related tutorials or talks, take a picture of this, look it up, and you'll find it on the schedule. You can reach out with the Kubernetes Storage SIG. We have bi-weekly meetings. We're on Slack. And we have a mailing list. So these slides are online on the schedule. You can download them and click on these links. Thank you so much for coming, and thank you for listening. Again, my name is David, and this is Jan. We're going to open up the floor for any questions now. First, you want to hold on to this?
Hi. With things like snapshots that might or might not work, is there any way I, as a user of the cluster, can find out if snapshots are going to work on the particular cluster I'm deploying on?
So the question is, if as a user, is there any way to know whether snapshots will work for the storage that I'm using?
So is it in the storage class?
It's not anywhere. It's not in the storage class. It's not in anywhere. You just try, and it will fail. It should be in the documentation provided by your cluster admin.
Right. Your cluster admin should provide that documentation for you. Yeah, any bugs you want to file, any issues you have, you can file them on Kubernetes, and tag SIG storage in them. All right, any other questions? I saw this hand go up.
So can we make the port to the local volume to cloud storage? So I mean when we create the persistent volume inside in the local, and then write something, and eventually copy to the cloud storage, like Google or AWS, and then my question is, can we mount the copied volume as a new persistent volume in the cloud?
I'm not sure I understood the question.
If I could try to rephrase, were you asking if a pod writes to a local volume and then we copy that data to a cloud volume, then can we then mount that cloud volume into a different pod or back into the same pod? In any pod? Okay, yeah, so I think we can just break this down into two separate steps, right? The pod writes to the local volume. You just use all of the Kubernetes concepts we've covered to mount that and use your local volume. Copying the data to the cloud, I think that's a separate operation that you would do outside of Kubernetes, kind of, right? And then mounting that cloud volume to a pod again is just using the same, the basic concepts to just create the PV for that cloud volume, create a PVC that then references it, and then consume that by your pod. Does that answer? Right. Any other questions?
Hi. I would like to ask, so we have a particular situation. We have an NFS storage that we want to present to a Kubernetes cluster, but it's very particular. Every directory needs to be accessed only by specific namespaces. So basically, we want a namespace to be able to mount one and only one directory within this storage. So as far as I know, persistent volumes cannot be bound to namespaces, and we cannot create a storage class because for host path, it's not supported. So for now, the only way we can control this is using pod security policies and preventing the prefix of the path to each user that is connected to each namespace. But this is a very complex solution for a very kind of simple problem. So is there an alternative way to make sure that a particular persistent volume is mounted only by a specific namespace?
There is no easy solutions. There is no easy solution. Persistent volumes are sort of global for everybody. We don't restrict them by namespace. But what we do restrict are storage classes. So maybe we didn't say it during the talk, but you can restrict a storage class with quota and give access to a storage class only to one namespace. That's possible. But then, in your case, you need to create a namespace, a class for each namespace. I don't know how many namespaces are you going to have. If it is few, that it's probably feasible. If it is thousands, maybe you need some operator that will pre-create it for you or something like that.
All right, we're out of time for questions now. Thank you so much for coming, and have a great rest of the day.